Hey everyone, welcome back to Strange New Worlds, a science and Star Trek podcast. I'm your host, Mike Wong. So last year, in 2024, I went to many conferences, but two of them were especially mind-blowing. In April, I had the pleasure of being invited to the conference called Earth at the Crossroads, a collaboration between the SETI Institute and Georgetown University here in DC, where I live. This conference was all about how studying other planets might help us save our own. And I was invited to give this review lecture on exoplanet science and looking for life elsewhere in the universe. And this conference left me feeling so optimistic, more optimistic than I had ever felt leaving an academic gathering, because I was surrounded by all of these people who got together for 3 days to talk about how we're actually going to make it, how we're going to get out of the climate crisis, and how my research as an astrobiologist can play a small role in all of that. But as that optimism overwhelmed me, I also started to feel guilty, because this sense of optimism that I felt coming out of this scientific conference was something that only a select few people can enjoy. Meanwhile, the climate crisis is still raging. People are suffering. And here we were, happily talking about the possibility of solving the crisis and feeling good about ourselves for doing it. But what will we actually do? Half a year later, in November, I was again invited to a brilliant conference called the Planetary Summit. This one was held in Venice by the Berggruen Institute to talk about the concept of what they call the planetary. That's how we've got to transcend local and national boundaries in order to tackle challenges that are literally globe-spanning, like climate change, again, but also things like pandemics and pollution. Once again, this conference was a stunning mix of thinkers and doers, academics ranging from political scientists to historians to philosophers, and also scientists like myself, people who studied astronomy, biology, earth science, plus people from industry and government. And again, I was awash in this optimism, because here were a bunch of smart, talented, dedicated, creative people who want to make the world a better place. And again, after the optimism seeped all the way through me, a twinge of guilt. I mean, look, here we are, scholars of all kinds talking about, but only talking about, how we're going to fix the world's problems. What are we actually going to do? What am I actually going to do? It is because of these two extremely invigorating, but also oddly guilt-tripping conferences that I went to last year, that I decided that every talk that I give in the future about exoplanets can also be a talk about climate change. And here's why. In exoplanet astrobiology, one of the first-order questions that we want to know about some faraway world is whether or not it's habitable. An exoplanet's habitability is an assessment about whether or not life can survive, proliferate, evolve, and thrive on another world. Habitability for exoplanets is actually assessed using many of the same tools and methods that we have developed to address climate change. The numerical models that we use to simulate Earth's changing climate can be tweaked just in a different way to simulate the habitability of an exoplanet. Also, our future as a civilization is very much relevant to astrobiology, our search for new life and new civilizations in the universe. And so, spurred by this desire to do something as a result of having gone to these two conferences, I decided to craft a brand new public science talk, which I gave for the very first time to the Royal Astronomical Society of Canada when I visited Montreal in early 2025. Now here I want to give a big shout out to my friend and colleague Emily LaFlèche for arranging that talk, and to Kareem Jaffer for hosting me. Now I just loved giving that talk so much that I decided the day after to turn it into a magazine piece, which I published in Noema magazine this summer. So today, on Strange New Worlds, I'm going to read that piece. It's titled, "What Searching for Aliens Reveals About Ourselves." And it's all about how looking for life beyond Earth, how my job as an astrobiologist changes the way that we all perceive life right here at home. Ready? Engage. What searching for aliens reveals about ourselves. Looking for life beyond Earth changes the way we perceive life right here at home. By Michael L. Wong, published July 30th, 2025, in Noema magazine. As an astrobiologist, I am often teased about my profession. Some people believe that astrobiology is just a catchy buzzword used to garner headlines and secure funding. Others view it as mere science fiction, or worse, a pseudoscience, because it lacks a subject of study. The most common question I get about my field is, how can you even do astrobiology when you haven't found life in space yet? My answer is always the same. But we have found life in space. People's eyes widen as they wait for me to divulge state secrets about where we're keeping the alien bodies. But the truth is far more down to earth. You are life in space, I say. We are all life in space. The moment we realized our entire biosphere existed on the skin of a rocky planet hurtling through the void around a very ordinary star, one of some 100 to 400 billion stars in our galaxy, which is one of perhaps 2 trillion galaxies in the universe, we discovered life in space. The exciting question for astrobiologists today is, could there be more of us out there? Astrobiology seeks to uncover generalizations about life, how it comes about, where to find it, and what it is in the first place. Because we are part of the set of all living things in space, astrobiological progress reflexively reveals new truths about us. Even if we never find life out there, the search itself shapes how we understand our own stories right here on Earth. Astrobiology is more than just a buzzword or an idle fancy. It is the key to developing a sense of belonging as a planetary phenomenon. Over the last 3 decades, our discoveries of exoplanets, planets orbiting stars outside our solar system, have revealed that there are likely hundreds of billions of worlds in our galaxy alone. Most exoplanets are far from hospitable for life as we know it. These include so-called hot Jupiters, gas giants orbiting so rapidly that one of their years can occur in just a handful of Earth days, with temperatures in the thousands of degrees, as well as colder Jupiters, which may resemble the gas giants of our solar system, and rocky planets so hot that their surfaces are oceans of molten magma. Astrobiologists, however, are more interested in the at least 24 worlds that we know of so far that are just the right size and distance from their host stars to potentially support life as we know it. The first clues about an exoplanet's habitability come from its atmosphere. After all, a thin sheath of gas makes life possible at the surface of our world, providing essential nutrients for the biosphere, protecting living things from harmful radiation, cycling water around the globe, and keeping global temperatures in check. Luckily, atmospheric chemistry is one of the most readily observable features of an exoplanet. In most cases, the gases in its atmosphere leave their fingerprints in the starlight that reaches the range of our telescopes. With state-of-the-art technology like the James Webb Space Telescope, we have confirmed the presence of carbon dioxide, sulfur dioxide, and methane on hot, gaseous worlds that are incompatible with life. These are molecules you might also expect to find on living planets. You breathe out carbon dioxide, the archaea in your gut emanate methane, and volcanoes belch sulfur dioxide. But to observe gases like these on Earth-like planets, small rocky worlds with razor-thin atmospheres, we require a new technology of perception, the Habitable Worlds Observatory, or HWO. HWO is, for now, only a telescope concept, a mere glimmer in the eyes of astrophysicists around the globe. Planned to launch in the early 2040s, it would be humankind's first scope designed specifically to hunt for signs of life beyond our solar system, surveying roughly 24 potentially habitable exoplanets for the exhalations of alien biospheres. The current schematics, though presently in flux, detail an instrument of unprecedented scale and power. HWO will be equipped with a 20 to 26-foot diameter mirror and a sophisticated coronagraph that suppresses starlight, enabling us to image the faint light reflected off Earth-sized planets. Its spectrometers will sweep wavelengths from the deep ultraviolet, through the visible, and into the near-infrared, so as to gather a complete census of biogenic gases in a planet's atmosphere, from oxygen and ozone, which absorb UV and visible light, to water vapor, carbon dioxide, and methane, whose spectral features lie in the infrared. But until HWO launches, to the best of our knowledge, most rocky exoplanets in the galaxy will remain Earth-sized blank canvases upon which we imagine exciting possibilities. Like science fiction writers, astrobiologists play what-if experiments, except our stories aren't written in prose, but in computer code. Astrobiologists assess exoplanet habitability using tools climate scientists have developed to predict Earth's changing climate, and that planetary scientists have used to investigate the climates of other solar system worlds. We take a known model of the Earth, Mars, or Venus, for example, and tweak it. For example, changing its atmosphere, the ocean-to-continent ratio, the star that it orbits, or the tilt of its axis, so that it now captures the processes of a more distant planet. While many of our simulations will be mere fictions, what makes them scientific is that these thought experiments are constrained by the known laws of physics, chemistry, and biology. In the end, we produce scores of imaginary worlds that give us clues about what we need to look for to find another Earth-like planet using future observatories like HWO. This is because hunting for another Earth means searching for many different things. Earth has been many planets throughout its 4.6 billion year history. It is believed to have started out as a hellish, volcanic world of blackened basalt. After the first oceans condensed onto the surface and life took hold, it may have appeared as a pale orange dot, thanks to a thick layer of organic haze. Later, it may have looked distinctly purple, due to the pigments of early photosynthetic life. We know from the rock record that Earth went through global glaciations, the Snowball Earth episodes, during which it would have gleamed like a pearl in space. And now, it is a beautiful blue-green marble. The steps our planet took to reach its current form may be unique. Different initial conditions and co-evolutionary tangos with life could have resulted in completely novel planetary stories. Earth is a beautiful contradiction. at once a multitude of different worlds, and just one evolutionary trajectory of an inhabited planet. Planetary scientist Jonathan Lunine captures this sentiment poetically in Astrobiology, a multidisciplinary approach. Lunine writes, "The Danish Prince Hamlet in Shakespeare's play of that name admonished his friend Horatio. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy." Today, we might instead warn ourselves of the likelihood that there are more kinds of Earths in the heavens than are dreamt of in astrobiology. Although many exoplanet scientists describe their work as a search for Earth 2.0, I find this phrase extremely misleading. Earth 2.0 conjures images of a literal copy of the Earth, but we're not looking for an escape hatch after we've trashed version 1.0. What then are we searching for? In truth, Earth 2.0 is not a place, but a revised concept of what an Earth-like planet is, and what it might mean to find one. When you hear the term Earth-like planet, what do you see in your mind's eye? An astronomer might see a planet with a certain mass, radius, and density. A geoscientist might care more about the planet's interior structure, its tectonic state, and its mineralogy. An astrobiologist might be very concerned about whether it has held on to an atmosphere and supports a liquid water ocean. A biogeochemist might say it's not an Earth-like planet unless it has a thriving biosphere. All of the above define Earth-likeness via intrinsic properties. The planet must have this, or must be like that. But what if Earth is better described by its relational properties? Investigating how planets and their biospheres co-evolve helps us understand living worlds as intricate webs of connections and interactions, and the role we play within it. The suggestion that relational properties could be important to Earth-likeness is hardly radical, considering that the International Astronomical Union's 2006 definition of a planet contains 2 relational criteria and just 1 intrinsic criterion. First, a planet must be in hydrostatic equilibrium, meaning it has enough self-gravity to pull itself into a fairly round shape. This intrinsic criterion rules out small, irregularly shaped bodies like asteroids and comets. Second, a planet must orbit the Sun. This relational stipulation rules out moons. Third, a planet must be gravitationally dominant in its neighborhood. This relational provision is why Pluto no longer qualifies. Even the ancient Greeks identified planets as heavenly bodies wandering the night sky relative to fixed stars in the background. That's a relational criterion too. In relational terms, Earth-likeness could be defined by the existence of ecologies of systems within the planet itself that interact with each other in self-promoting ways. For example, Earth's water cycle, plate tectonics, core-powered magnetic field, and carbonate-silicate weathering feedback loop are all intricately intertwined through complex causal couplings. Water lubricates fault planes and lowers the viscosity of rocks and may play a crucial role in maintaining plate tectonics on Earth. Because plate tectonics expedites heat loss from the planetary interior, it may contribute to maintaining the vigorous core convection required to sustain a planet's magnetic dynamo. The dynamo produces a global magnetic field that can shield the planet's atmosphere from erosion via solar wind, helping a planet retain its atmosphere. Finally, the atmosphere serves to buffer the planet's surface temperature through the carbonate-silicate weathering cycle so that the water cycle can persist. Together, Earth's planetary processes have conspired to maintain its activities. They function in concert as a dynamically persisting network of interactions. In this framework, we might see life as something that emerges on the planet, intertwining with its environment in a self-promoting feedback cycle. A good example of this involution is the little-known connection between temperature regulation and woolly mammoths. During the last ice age, woolly mammoths roamed Earth's northern reaches, including the region of the world we now call Siberia. Through their grazing, they cycled nutrients that promoted the replacement of forests with Arctic grasslands. Their stomping also compacted freshly fallen snow into stable permafrost, which persisted even in the summer months thanks to the insulation provided by the grasslands. Arctic grasslands efficiently sequestered carbon from the atmosphere, and the permafrost reflected solar radiation back to space. Thus, some researchers think that mammoths played an essential role in maintaining the tundra. Through their interactions with the environment, they effectively maintained a cool climate, conditions in which they thrived. Until, of course, we came along. Although early humans were probably not the sole reason why woolly mammoths and other large steppe animals went extinct, hunting played a large part in their demise. Without the mammoths to graze and stomp, the Arctic's grasslands and permafrost began to shrink. When land absorbs more radiation and captures less carbon dioxide, runaway feedback exacerbates rising temperatures. Today, the warming of the Arctic tundra could release disastrous amounts of carbon, frozen in its shallow subsurface for millennia, into the atmosphere. Indeed, it has already started. Although climate change is generally concerned with the past 300 or so years of industrial activity, humans began to profoundly affect Earth's climate many thousands of years ago. For this reason, some argue that the Anthropocene, a proposed new geological period defined by our species' emergence as a global force, should not be demarcated by the onset of fossil fuel burning, the isotopic variances induced by nuclear weapons testing, or the plastics that will inevitably gum up the rock record, but by one of our earliest influences on Earth's climate via contributing to the eradication of gentle giants like woolly mammoths. Modern science has allowed us to better understand how far-reaching the consequences of our actions can be. Science not only develops the instruments we need to peer into the cosmos, but it also creates the tools we require to diagnose more down-to-earth matters. Many of the satellites we launch into space look back at Earth, monitoring our weather and climate. Even certain telescopes perched atop Earth's mountain peaks for the astronomical benefits of rarefied air are pointed downward to study changes in our own atmosphere. These technologies of perception grant our world a degree of planetary sapience, a kind of self-knowing that is unique, as far as we can tell, to Earth. The same principles that allow us to hunt for alien Earths also allow us to comprehend the biosphere as a planetary phenomenon. We are the part of Earth that has learned to understand itself. As myriad ecological crises unfold around us, one question plagues me. Will we be able to reorient toward planetary homeostasis in time? One might think this concern, which fits squarely in the realm of climate research, Earth system science, and environmental policy, has little to do with my work as an astrobiologist. But it is extremely relevant to the search for life elsewhere. After all, one thing we astrobiologists want to know is, where is everybody? Known as the Fermi paradox, after the physicist Enrico Fermi, who famously posed the question to his colleagues over lunch one day in 1950, it is a conundrum that reflects the apparent tension between the conspicuous absence of intelligent life in space and a universe that appears amenable to its origin and evolution. One answer to the Fermi paradox is that what we call intelligent life isn't really that intelligent at all. There's a humorous take on the habitable zone drawn by space artist John Lomborg that depicts Venus, Earth, and Mars orbiting the Sun. Venus is labeled too hot, Mars is too cold, and Earth, too dumb. The comic suggests that while oases for civilized life may be common, civilizations themselves may be too inept to persist. Whether Lomborg's depiction represents reality has profound consequences for the number of alien civilizations we should expect to exist out there. In 1961, astrophysicist Frank Drake developed a simple equation to estimate the number of intelligent transmitting civilizations in the Milky Way galaxy. Some of its terms, like the rate of star formation and the fraction of stars with planetary systems, are quantifiable thanks to modern astronomy. Other parameters, those dealing with the emergence and evolution of life, are far more uncertain. The final parameter for the Drake equation is the lifetime of technological civilizations that release detectable signals of their existence into space. Do they typically exist for a mere blip, multiple millennia, or a geologic age? This last variable, denoted by a capital L, has the potential to sway our results from astrobiopessimism to a universe teeming with cosmic pen pals, or vice versa. A few years ago, my colleague Stuart Bartlett and I argued in a paper that this L variable is likely a bimodal distribution, like a camel's double-humped back. There's likely to be one pileup of civilizations that don't last very long, those that were too dumb, and a second pileup of civilizations that somehow figured it out, so to speak. Those civilizations that figure it out are likely the ones that come to understand that they are an integral part of nature. Modern society instills in us a kind of human exceptionalism, the belief that we are separate from and above nature. We tend to think that we can extract whatever we want from nature, that civilization is born from the ability to force the wilderness into submission. But the more we listen to science, the more we realize how intimately entangled we are within the natural world. We are connected by the generative threads of cosmic evolution to nebulae and stars and the Big Bang itself. We are Earthlings, much like the mantis shrimp, giant sequoia, and the Himalayas. Yes, humans exert a profound influence on the rest of this ecological web, but the harm we inflict on our environments will come back to bite us. When we awaken to the reality of our deep entwinement with the rest of nature's forces, we might consider revising the Arthur C. Clarkeism that, quote, any sufficiently advanced technology is indistinguishable from magic, end quote, to any sufficiently advanced civilization is indistinguishable from nature. Doing so could completely revise our search for advanced life, which is largely based on the search for alien technology. But conflating intelligence and technology is an assumption worth challenging. True intelligence may know not to use the technologies we so dearly cling to as we plumb our planet's riches to exhaustion. The modus operandi that has brought us to the brink of nuclear annihilation and plunged us into a global climate crisis may not be a recipe for cosmic longevity. Instead, the next phase of civilization's evolution might require a radical adjustment toward prioritizing planetary homeostasis. If so, then perhaps a thriving Earth-like world is unlikely to spawn a galactic empire that colonizes other worlds, or exhibits anything like the extractive and greedy imperialism seen in a small range of human cultures over the last 500 years, or even longer. Fermi's question presents itself as a paradox only under the implicit assumption that the future is a linear extension of past and current trends. But science teaches us that evolutionary history is rife with major transitions to brand new states of being. Eukaryogenesis, multicellularity, sociality. Perhaps self-awareness-driven reprioritization towards planetary homeostasis may be the next transcendence that life takes, or must take, after civilization as we know it. Perhaps the Fermi paradox is not really a question of where is everybody, but what is everybody now? The most brilliant night sky I've ever seen was on a backpacking trip in the Grand Canyon. Shielded by the canyon walls, there was hardly a trace of light pollution. You could see the Milky Way stretch across from one side of the canyon to the other. Even Andromeda, our neighboring spiral galaxy, was visible to the naked eye. Seeing the universe in its full glory was, as novelist Sherry Thomas once put it, like witnessing a diamond heist gone awry. Gazing upward, I couldn't help but be reminded of how much there is to learn from asking questions of the cosmos and our place within it. Astrobiology teaches us about our strengths, which derive from relationships that are both obvious and subtle. It teaches us about our fragility. Just around 62 miles of air separates us from the blackness of space. From it, we learn more about where we came from, our humble beginnings as single-celled organisms swimming in Earth's early oceans, and who we are, whether incessant explorers, persistent dreamers, or inevitable storytellers. Astrobiology teaches us about our planetary belonging. Earth is our home, a pale blue dot that serves as our perch for peering into the cosmos. But above all this, the study of the stars tells us who we must become. Searching for alien life is not an activity that yields instant gratification. It may take centuries or even millennia to find what we're looking for, and millennia more to hold any meaningful conversation with whatever intelligences exist. But to give ourselves the best chance of finding alien life, we must become a long-lived civilization ourselves. We must become the hope we wish to see in the cosmos.